Welcome to our presentation. I'm going to introduce our work on generalized tangent kernel, a unified geometric foundation for natural gradient and standard gradient. This is a joint work done by Qingxun Bai, Steven Rosenberg, and Wei Xu. Our problem setup is the supervised learning of a function f, say from Rn to Rm. In particular, we consider parameterization of the function f with a mapping phi from the parameter space W to the function space big M. For the supervised learning, a loss function f is defined on the function space big M. Then, as shown in the commutative diagram, f and phi introduce a loss function f tilde on the parameter space W. We use this 2D picture to intuitively illustrate our setup in a high-dimensional space. Phi maps the parameter space W to parameterize the function space phi of W embedded in big M. We use big phi to denote this embedding, and big M is a so-called ambient space. For instance, if phi is some specific neural network architecture, say AlexNet, then it maps the set of parameters to the space of neural network functions. Given that big M is the space of all maps from input to output, the parameterized function space of all possible AlexNets, phi of W, has to be a subset of big M. We use a curved gray surface in big M to illustrate this parameterized function space, just to highlight that map phi can be nonlinear, just like neural networks. For the purpose of supervised learning, a simple strategy is to directly do gradient descent on the parameter space W following the gradient of f tilde. However, for natural gradient, we care about the actual gradient direction on parameterized function space big phi. Following this diagram, first, some gradient of f has to be computed on the tangent space of big phi. Then this gradient will be pulled back to the parameter space W to get the natural gradient. However, a key argument of ours is that the gradient of f need not lie in the tangent space of big phi. As shown in this picture, it could point to any direction in the ambient space big M. As a result, what we need first is an approximation of grade f on the tangent space of big phi before pulling it back to W. But most existing work on natural gradients focuses on the red dashed region in this picture, that is, pulling back the loss gradient from the tangent space of big phi to the parameter space W. In this work, we provide a more complete study of projective functional gradients, which analyzes both the gradient of f on ambient space M and its projection onto embedding phi, before pulling it back to W. In particular, we first discuss an overlooked issue regarding the existence of grade f on the ambient space M. After addressing this issue, we then study carefully the analytic and differential geometric properties of the projection of grad f from M to the tangent space of phi. As we will see, our unified framework and analysis apply to natural gradient, standard gradient, and beyond. Our first resort is a projection view of natural gradient. We put a typical natural gradient descent update formula here for reference. We show that the appearance of the inverse symmetric matrix in natural gradient is in fact a consequence of the orthogonal projection of grad f from M to big phi. As shown in this equation, the left-hand side is the orthogonal projection of grad f from M to the tangent space of big phi. In order to compute this projection, we need some basis on the tangent space of big phi. Since ddwi is the default coordinate basis on the Euclidean space W, the corresponding push-forward basis on the tangent space of big phi is just d phi dwi. Using this default push-forward basis to compute a projection of grad f, we get the right-hand side of this formula, which is exactly the standard natural gradient formula. Here we use G tilde lower ij, which is not shown here, to denote the corresponding metric matrix, and G tilde upper ij as shown here to denote its inverse, just like A inverse. Our projection view also gives another equivalent formula for natural gradient. If given an orthonormal basis hi on the tangent space of big phi, we can have a simpler projection formula where the metric matrix becomes identity matrix. We have been talking about natural gradient, but how about standard gradient, which is the default gradient used everywhere in machine learning? It is actually a surjection of grad f from M to big phi, instead of a projection as in the natural gradient case. Again, this surjection can be represented in the right-hand side of this formula using the push-forward basis d phi dwi. This formula implicitly uses the following metric on the tangent space of big phi, that is, inner product of d phi dwi and d phi dwj equals delta ij. This is actually the push forward of the Euclidean metric from W to phi, because in the Euclidean space W, by default, we have ddwi inner product ddwj equals delta ij. However, unfortunately, this metric is in general not true, because d phi dwi is, in general, not an orthonormal basis of the tangent space of embedding phi. That's why, in general, the surjection S is not a projection, which definitely loses extra information about grad f compared to a projection. So far, our projection view is consistent with the conventional wisdom that regardless of computational cost, natural gradient has an advantage over standard gradient in capturing the geometric structure of the immersed function space. But we will see some surprising results later that challenge this conventional wisdom. Before that, let's first take a look at the long overlooked theoretical issue for natural gradient. Does grad f exist on the ambient function space M for common choices of the metrics in supervised learning? To be specific, the ambient function space M is an infinite-dimensional vector space. Gradients on the space depend on choice of metric. Some common choices include L2 and Fisher-Rao. In supervised learning, f is actually some empirical loss function given some finite set of training data. Let's take a typical choice of empirical loss with MSE as an example. Xi, Yi are training sample pairs. We show in this work that a formal computation under the L2 metric gives this gradient formula, where delta I is the delta function at xi. By formal, we mean mechanical and not being rigorous in a mathematical sense. Because, as we know, delta functions do not exist in L2. As a result, L2 gradient of empirical MSE loss does not exist in the function space M. In fact, this result is general and fundamentally caused by the discrete nature of empirical loss. As shown in our paper, L2 gradient of any differentiable empirical loss is formally a sum of delta functions. We also show a similar result for the popular Fisher-Rao metric for classification functions. Again, the gradient is formally a sum of delta functions, which do not exist in the space of probability distributions. Note that Fisher-Rao is the metric Murray used to derive the original natural gradient. The non-existent issue of natural functional gradients motivates us to study this problem in RKHS, which by definition is a function space where delta functions are continuous. For a general differentiable function L, where Z and W denote predictive output of the training function and ground truth respectively, Let nabla E L Z denote the Euclidean gradient with respect to Z. Recall our formal computation of gradient in L2, which give the sum of delta functions. Now in an RKHS H with kernel KH, it becomes a sum of evaluation functions defined by the kernel. As a result, we get this well-defined kernel representation of functional gradient. After addressing the existence issue of the functional gradient in ambient space M with RKHS theory, we can proceed to define the corresponding natural gradient following our projection view. Recall the previous projection formulas of natural gradient using the default push-forward basis and the orthonormal basis on the tangent space of the embedding phi. We then apply this projection to the kernel representation of the functional gradient we just obtained. We end up getting this kernel formula of natural gradient, where Kf here is the projection of kernel Kh onto the tangent space of embedding phi, which itself is also in RKHS. In fact, the projection view produces a family of projected RKHS parameterized by the parameters in W. Similar as the projection formulas of natural gradient, this projected kernel Kf can also be represented using a different basis of tangent space of phi. We list here the formulas using a default push-forward basis and orthonormal basis respectively. So far, we have combined our projection view and RKHS theory to obtain kernel representations of natural gradient. Can we get a kernel representation for standard gradient? Recall that instead of the projection view, we have introduced a surjection view of standard gradient. Again, it is the standard gradient used everywhere, and it uses default push-forward basis on the tangent space of embedding phi. Similar as in the natural gradient case, we apply this surjection to the kernel representation of functional gradients. Then we end up getting this kernel formula of standard gradient. Theta here is a kernel defined by the push-forward basis. This kernel is known as the neurotangent kernel. Now we have obtained the kernel formulas for both natural gradient and standard gradient. The only difference lies in the kernel. So let's take a closer look at the two kernels. They are of the same form, but with different bases on the tangent space of big phi. That is, the orthonormal basis and the default push-forward basis. This observation motivates a generalized kernel form, which we define as the generalized tangent kernel. For any basis Bi of the tangent space of embedding phi, its corresponding GTK is defined like this. Then Kf and theta are just two special cases. When GTK is defined from the orthonormal basis, we get Kf, which corresponds to natural gradient. When GTK is defined from the default push-forward basis, we get the NTK, theta, which corresponds to standard gradient. Now comes the most important result of this work. The reason for introducing GTK is actually beyond formally unifying natural gradient and standard gradient. More importantly, it enjoys a very appealing property that leads to surprising new understandings of natural gradient, standard gradient, and beyond. As has been discussed so far, given an arbitrary basis, say Bi, on the tangent space of embedding phi, in general, there is no reason that this basis is an orthonormal basis, such as the default push-forward basis. However, with GTK, we can show this automatic orthonormality property. For any basis Bi of a finite dimensional function space, make this function space an RKHS by using the GTK defined by Bi as the reproducing kernel, then Bi becomes an orthonormal basis of this RKHS. With this appealing property of GTK, we can define a valley natural gradient using the projected kernel formula from an arbitrary basis of the tangent space of embedding phi. Recall the previous projected kernel formula of natural gradient. We can simply replace Kf with the GTK from any basis. Because of the automatic orthonormality of GTK, any basis Bi guarantees an orthogonal projection of functional gradient from the ambient space M to embedding phi. The GTK theory provides new understanding of natural gradient, standard gradient, and beyond. In particular, there exists a family of projected functional gradients on the tangent space of embedding phi. Each of these projected functional gradients produces a natural gradient that reflects a well-defined geometric structure. This is in contrast to the conventional wisdom that natural gradient has an advantage over standard gradient or other gradients in capturing the geometric structure of the function space, which was exactly the reason why it was called natural gradient. Now we see that, at least locally, the whole family of projected functional gradients given by GTKs are all natural. It also sheds light on why standard gradients work so well in modern machine learning practice, while the advantage of natural gradient is often minimal in practice. As we have seen, standard gradient is just the simplest example of this family of natural gradients given by GTKs. This framework also provides a practical and unexpectedly flexible way for defining new natural gradient variants in practice. Just use any basis on the tangent space at big phi. We will see an example leveraging this property in the next few slides. It is also worth noting that while GTK is a generalized form of NTK, the theory developed in this work does not correspond to any known results about NTK. Now we show an example application of the GTK theory to provide a new solution to the degenerate natural gradient case. Throughout our previous discussions, we have assumed that the mapping phi from the parameter space to the function space is an immersion. Otherwise, the pullback metric matrix G tilde lower ij becomes singular, and as a result, the inverse matrix G tilde upper ij in a natural gradient formula makes no sense. Such non-immersion cases of phi are actually not uncommon in modern function approximations. For instance, neural networks with any piecewise linear activation functions fall into this category, such as ReLU, leaky ReLU, shifted ReLU, parameterized ReLU, etc. And existing solutions use the Penrose generalized inverse to define a natural gradient for these cases. However, following our projection view, in general, it loses more information than an orthogonal projection. The GTK theory provides an alternative approach that guarantees orthogonal projection. The key idea is to leverage the flexibility of GTK in defining natural gradients. Here are the major steps of this approach. Step 1. Find a slice S of the parameter space W such that mapping phi restricted on S is an immersion. A slice S is a submanifold of W that has some technical properties. Please refer to our paper for more details. Step 2. Compute a basis Ci for each tangent space of S. Step 3. Choose the push forward of Ci as a basis on the tangent space of big phi. Step 4. Use the GTK corresponding to the push forward of Ci to obtain a well-defined natural gradient. It is worth noting that without the GTK theory, directly computing the conventional natural gradient on slice S makes little sense. Because the conventional natural gradient is known to be computationally expensive, and people rely on a series of approximations to make it acceptable in practice. Restricting the conventional natural gradient to slice S is even more complicated. In fact, it is unclear if a valid approximation still exists. We have applied this approach to MLP with ReLU activations. In our preliminary experiments on CIFAR-10, our approach works slightly better than the SGD baseline. While this empirical advantage seems marginal, it is worth noting that we have searched for the optimal settings for the baseline while simply aligning our approach with the baseline. It is also worth noting that the extra computational cost introduced by our approach, as shown in the plot, is negligible in practice. While our experiments are still preliminary, it shows the potential of the GTK theory while leaving a large room for practical optimization for future work. Here are some take-home messages to summarize this work. It provides a more complete understanding of the geometric foundation of projective functional gradients than has appeared in the machine learning literature. We believe that this is just the beginning of fruitful results in both theory and practice of a broader view of natural gradient. To list some future theoretical directions, the relation between choice of metrics via GTK and the convergence rate and generalization ability. And transformers are known to possess the in-context learning capability. It has been shown that transformers actually learn to implement preconditioned gradient descent for the forward pass. Then, is there a GTK explanation for this preconditioned gradient descending forward pass of transformers? To list some future practical directions, we want to study non-immersion function parameterizations beyond MLPs, say CNNs, ResNets, and transformers. It is also interesting to study a general approach to the slice computation for different neural network architectures. Thank you.